Hi, in this video, let's look at a sequence that does not converge, or in other words, the limit of the sequence does not exist. Let's also discuss a precise definition of limit of a sequence as an enrichment topic. So let's look at this sequence. 1, -1, 1, -1. You get the picture of how the elements of the sequence are written. This is, remember, an infinite sequence. And we claim it doesn't converge to any number. Another way of saying is that sequence is divergent, or the limit of the sequence does not exist. All three mean the same thing. So let us approach this as follows. So just looking at the sequence, it looks like, couldn't we say -1 and 1 are the limits of the sequence? Because somehow we find that there are an infinite number of elements that are crowding 1 and crowding -1. But if we look carefully at the limit of a sequence definition, we cannot claim 1 is the limit, cannot claim -1 is the limit either. Let's work on why 1 is cannot be the limit of the sequence. If you think 1 is the limit of the sequence, then if I mark off any neighborhood around 1, I'll mark off a very small interval around 1. We can call that a neighborhood, or if you can call that an interval around 1, an open interval. My question for you is, are you able to look at the sequence and tell me some cutoff point? By cutoff point, this is what I mean. This is the first element of the sequence, this is the second element of the sequence, third element, fourth element. So are you able to tell me, go up to, I'll just make up a number, 1000th term of the sequence. And then are you able to tell me that the first elements, we don't know where they lie, but everything else, the 1001th element, the 1002nd element, everything that comes later, are you able to tell me that all of them do lie in this open interval? The answer is no. Doesn't matter if it's the 1000th term, 10,000, a millionth term, no matter where you put that cutoff point. After the cutoff point, you will see either 1, -1 or -1, 1 as the next terms in the sequence. And clearly that -1, one of the terms of the sequence, it does not lie in this interval. It's not captured in here. So if in a minute we'll look at the precise definition of the limit of a sequence, which demands that if you claim a number is the limit of the sequence, then that property should hold. Which property? The property namely, if you pick any small interval around the number that you claim is the limit, then you should be able to find that cutoff point like the way I explained informally, and guarantee me that all the elements after that will lie in this interval. You're not able to do that for this. So 1 is not the limit. For the same reason, actually, no number on the real line is the limit. That's why the sequence does not converge to any number. So I hope that convinces you that even though you have an infinite number of numbers in the sequence that are exactly 1, and so they crowd 1, infinite number of them that crowd -1, still -1 is not the limit of the sequence, 1 is not the limit of the sequence. The sequence does not converge. That means the sequence is divergent, or another way of saying is the limit of the sequence does not exist. Now let's take a quick look at a precise definition of the limit of sequence. Here's a precise definition for limit of a sequence that one may see in an advanced calculus class that is being studied in a rigorous manner. If you're studying calculus more with an intuitive or an informal approach, then consider this an enrichment topic. So let's just dig deeper for the next 5 minutes or so. Let's read the definition together. A sequence x sub n is said to converge to a number L, which is usually called the limit of a sequence, if for every epsilon, this is a Greek letter, epsilon, positive, we can find a positive integer n based on epsilon, so that the following is true. N greater than n epsilon implies this inequality is true. So what is it really saying? So let's draw a picture to make sense of it. I've marked on this number line a number called L. if you claim that this sequence converges to L, that must mean something. And I want to explain to you what that means. Firstly, this sequence xn, let's write it out in this manner, expand it out. This is just a shorthand name for the sequence. These are all numbers. The first element's name is x sub 1, second element's name is x sub 2, and so on. What we are saying is, if we think the sequence converges to L, intuitively from the examples we've studied, we feel that these elements begin to crowd L. They're all very close to L somehow as you go down these numbers in the sequence. How do we say that precisely in mathematical terms? What this one is saying, this for every epsilon positive, epsilon is a very small number. What that is really saying is, okay, if we want to say the sequence converges to L, and that means the elements crowd L, let's pick a very small interval, open interval around L. That's what this is telling you. This epsilon is just a name for something very small. So I've created an interval around L so that this like this epsilon and this like this epsilon. And now what we are saying is, if we want to claim that these elements crowd L, another way of saying that is, based on how far out this interval is, if we can find a positive integer, this one may be very large depending on this, but it is still a positive integer, such that if you begin to look at the index or subscript of these elements, if we are able to say, ignore the first finite number of elements in the sequence, in this case we're marking them as x1 through xn epsilon, but after that the rest of them we are saying should lie in this interval. If that happens, then we are saying the sequence converges to L. So this whole argument should be true no matter how I create the red small interval around L. If you're able to find me this positive integer n based on this red interval, of course, and if you can find me that, and if you can guarantee to me that if you look at the elements of the sequence and if you look at their indices, all the elements of the sequence with an index higher than this n epsilon and greater than n epsilon, so that means these guys precisely, if you can guarantee those will be captured in this neighborhood, that's what this is really saying, then we get to say the sequence converges to L. So that is the precise definition. You can still continue thinking about limit of sequences more on the intuitive level. If so, what you need to think about is this sequence converges to L means here's L, elements of the sequence crowd L, in the sense that if you pick a small neighborhood like this red interval around L, somehow you're able to say there's a cutoff point where the first finite number of elements, you don't know where they are on the number line, but everything else is in fact in here. So that concludes our digging deeper into the definition. Let's go back and look at one more example. And now finally this trivial example. This is a sequence where every element is exactly 1. This is in fact convergent and it converges to 1. Maybe that was real clear to you that the limit of the sequence is 1, then all is good. And how do we justify it using the definition that we just learned? Well, let's go back here. Why is 1 the limit? Let's take a very small neighborhood around 1. This is the epsilon neighborhood or an open interval around 1. Can you tell me a cutoff point? Say, after the 10th term, after the 20th term, whatever you want to say, so that all the elements of the sequence that come after that cutoff point will lie in here. Well, guess what? We don't need to worry about any cutoff point. Every element of the sequence, in fact, lies in here. So if someone really asks you for a cutoff point, you can say after the first element or the second element, it doesn't matter what number you pick for your cutoff point. But you can see everything if I say look only after the second element, you can see we don't worry about where those two elements lie, but everything that comes after it fits into this. So the sequence is convergent. Thank you.